Welcome to Maths with EJD. We're still talking about partial differential equations, and for now, had considered the finite difference method for solving partial differential equations, finite difference method, or rather methods. Then there is the finite element method, which is the subject of consideration in this video, the finite element method. Then after now, we'll be talking about the spectral methods that requires a basis function like Fourier, Legendre, or Chebyshev spectral methods. Okay, so like I said already, we've done this. Now we are going for finite element method. Let's go. Finite element method. If you like FEM. So the finite element method is a numerical technique for solving PDEs. It works by breaking a complex domain into smaller, simpler elements, and approximating the solution over these elements. The finite element method is particularly useful for problems with irregular geometries, complex boundary conditions, and varying material properties. Okay, so next consider um let's consider steps of FEM, steps of finite element method. So the first one is the discretization of the domain. So for finite difference method also, we have discretization involved. So discretization of the domain. So we say the domain omega is divided into finite elements. That's where the name comes from. It is divided into finite elements, e.g., line segments can be a finite element in one dimension. We can have triangles. We can have triangles in 2 dimensions, and we can have tetrahedra in 3 dimensions in 3D. Okay, so you have so if you are talking about 1 dimension, so you can have a number the domain divided into several lines. In 2 dimensions, you can have the space divided into several triangles, tetrahedra, then in 3 dimensions. So nodes are placed nodes are placed at element corners. Nodes are placed at element corners or inside elements for higher order approximations. So that's the first step in that process. And the second step would be about choice of basis function. Choice of basis functions. As you're going to see later, spectral methods also require basis functions, just like I tried to explain earlier. So you have choice of basis functions. So the approximate solution UH of X is expressed as a linear combination, of basis, or what you can call shape functions. Basis of shape functions, which is phi I of X. Like this, you have U sub H of X equals summation from I equals 1 to N of U I phi I of X. So you have it as a summation of all those several basis functions, right? Where UI are the unknown nodal values. So that is step 2. Talking about step 3, we have what you call the weak formulation, or the variational form. So here you multiply the PDE by a test function, V, and integrate over the domain omega as follows. So you have integral over the domain, then you have L, let me see. I need to write this. L is special. Let me just write it this way. L of U sub H multiplied by V d omega is equal to integral over the domain omega of FV d omega. Something like this. Okay. So now we have L coming into this, where that L is the differential operator. It's the differential operator of the PDE. Then next, using integration by parts, I dealt with integration by parts under basic calculus. That's one of the earlier playlists which you can find every step broken down. Using integration by parts, when necessary, depending on what you have, when necessary. So you reduce the order of differentiation on U sub H. Okay. And then that takes us to the next one. Number 4, we have assembly of the system of equations. Since you have everything in several finite elements now, you have to get to a point where you put it all together. So the first thing is substituting, substituting basis functions into the weak form leads to a system of algebraic equations, which is Ku equals F. Ku equals F, where K is the stiffness matrix, and that depends on basis functions and PDE. Then you have U, which is the vector of unknown nodal values. And lastly, you have F, which is the force or load vector. All right, that's step 4. I mean, PDEs can be quite something because it's you have a lot to do. In step 5 now, you talk about application of boundary conditions. Okay, so this is essential. So essential Dirichlet boundary conditions are applied directly by modifying the system. Then you also have the natural Newman conditions. Natural Newman conditions appear in the weak form and affect F. Then number 6, so we talk about the solution of the linear system. Solution of the linear system. So the system is solved using numerical methods such as direct solvers, like Gaussian elimination, which we had considered in an earlier video, Gaussian elimination, or iterative solvers like conjugate gradients, or multi-grid, and all of that. So those are the steps here. Now that all of that is done, can we look at a worked example? Um, so solve the Poisson equation on the domain omega equals 0, comma 1. That's minus d squared u dx squared equals f of x. So you have u of 0. That is u of 0. So we have minus d squared u dx squared equals f of x with Dirichlet boundary conditions, u of 0 equals 0 and u of 1 equals 0. Actually, this should be written as partial, right? Partial squared u, partial x squared equals f of x, like that. So the idea is to solve using the finite element method with linear basis function. So we can go for that. So solution, we have the weak formulation. That's the first thing we take care of. So we go for, first of all, the weak formulation like we saw in the steps before now. So step 1, weak formulation. So for the weak formulation, we already said we multiply both sides of the PD by a test function v of x and integrate over the domain. That is integral from, that's integral from 0 to 1 of minus partial squared u partial x squared v of x dx v of x dx, and that is equal to integral from 0 to 1 of f of x v of x dx. So that's the first step here. Then the second step, we can do integration by parts. We have now integral from 0 to 1 of du dx, dv dx equals dx, and that's equal to integral from 0 to 1 of fv dx. You know, f of x, v of x dx, right? So here, boundary terms vanish due to the Dirichlet conditions, that is, we're talking about u of 0 equals 0 and u of 1 equals 0. So you see, because those ones are 0, right? So the boundary terms will automatically vanish because it's 0 in each case. So we move on to the next thing, and that is step 2, where we talk about discretization. So for discretization, we divide the interval, that's the domain we have, the interval 0, 1 into n subintervals, which you can call elements of equal length. So you have h equals 1 over n in that situation. H equals 1 over n. So these notes are x naught equals 0, x1 equals h, x2 equals 2h, all of that up to xn, which is equal to 1. You know, it's from 0 to 1. So then we approximate u of x as u sub h, u sub h of x, which is equal to summation from I equals 1, summation from I equals 1 to n minus 1 of ui phi 1 of x, okay, where phi I of x, rather, not phi 1 of x, phi I of x are piecewise, they are piecewise linear basis functions, linear basis functions defined as phi I of x equals x minus xi minus 1 all over h, that is xi minus 1 less than or equal to x less than or equal to xi. Then you have, okay, I guess I want to make this longer. Then we have xi plus 1 minus x all over h, where we have xi less than or equal to x less than or equal to xi plus 1. And finally, we have 0 otherwise. So that's how that function is defined. So that's that. You know, we also have ui, which we had talked about before. So you have ui. These are the ui are the unknown coefficients. Unknown coefficients, which are approximations. They are approximations of u of x are the interior nodes. Are the interior nodes. Okay, so we go for step 3. So step 3. Here we assemble, so we have assembly of the stiffness matrix and load vector. So substituting UH of x into the weak form, which we started out with, right? Into the weak form, we obtain the system of equations. The system of equations, summation from j equals 1 to n minus 1 of kij uj equals fi. That's like ku equals f that we talked about the other time. And that is 1 less than or equal to I less than or equal to n minus 1, where first the stiffness matrix K has entries kij is equal to integral from 0 to 1 of d phi I dx, d phi j dx, all of that dx. Okay. So evaluating this integral, evaluating these integrals for our piecewise linear basis functions, piecewise linear basis functions, we get a tri-diagonal matrix, which is K. Okay, I guess I better write the matrix first. So 2, minus 1, 0, all this down to 0. So all of that down to 0, right? Then we have minus 1, 2, minus 1, everything down to 0. Then we have all of that down here to 0, everything here, everything here. So 0, 0. Then we have, so this continues this way. We have -1, and this is -1, 2. So this 1 over h into this, all of this is equal to k. All right. So this is our k. And then we have the load vector. The load vector f has entries fi equals integral from 0 to 1 of f of x phi I of x dx. So if f of x is given, these integrals can be computed using numerical quadrature, which we have done before, numerical quadrature, like midpoint or trapezoidal rule, midpoint or trapezoidal rule. Okay, so that takes us to step 4. So for step 4 now, so solve the linear system, solve the linear system. So we now solve the system. KU equals F for U, which is U1, U2, up to UN minus 1 transpose using Gaussian elimination. Of course, this is too tedious to just be solved manually. So using Gaussian elimination or an iterative solver like the conjugate gradient method, for large n, use conjugate gradient method for large n. Then we have the approximate solution. Step 5, we have the approximate solution. So once U is computed, the approximate solution is UH of x equals summation from I equals 1 to n minus 1 UI phi I of x. So this function is piecewise linear and interpolates between the computed values, UI are the interior nodes, Hey, I'm trying to see. Okay, let's try to do a numerical example. So for the numerical example, so let's solve for minus partial squared U, partial x squared. F of x now is equal to 1. U of 0 is 0. U of 0 is 0. U of 1 is also 0. So here, using n equals 4, that is H now is equal to 1 over 4. The stiffness matrix is K, which is equal to 1 over H. That's like 1 over H. Talking about the stiffness matrix. From what we saw previously, K is all this stuff, right? So we just have 1 over H. Because we have 4 divisions, 1 over H. Let me see what is this here. Yeah, H is 1 over N. H is 1 over N. So since H is 1 over N, so it means that our K is going to be 1. So H itself is 1 over N, right? So we have 1 over H, which is 1 over 4. Really? It's 2, that's 2 minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 2. If you follow the pattern over there, and that's like, okay, I guess I can bring this down. Now that we have this, so K is equal to 4 into 2 minus 1, 0, minus 1, 2, minus 1, then 0, minus 1, 2. And finally, we can have K to be 8 minus 4, 0, minus 4, 8, minus 4, 0, minus 4, 8, like that. Because H is 1 over N. That's why 1 over H will be 4. So we have our H here now as this. Okay, so the load vector is Fi, which is integral from xi minus 1 to xi plus 1 of 1. You know, f of x is 1. So phi I of x dx. So all of this will be equal to h, which is equal to 1 over 4. That's like the load vector. Thus, we have f to be 1 over 4 into 1, 2, 1. That's 1, 2, 1. And that is equal to 1 over 4, 1 over 2, and 1 over 4 again, like that. So solving KU equals F, which is actually the same as 8 minus 4, 0, minus 4, 8, minus 4, 0 minus 4, 8, into U1, U2, U3, which is equal to 1 over 4, 1 over 2, 1 over 4. We want to check this out. So using Gaussian elimination, Gaussian elimination, we obtain U1 to be 0.09375. We want to check this, we want to confirm this 0.15625. I did not double check, so in case you find something amiss, please let me know in the comments. 0.09375, 0.09375. So we can then say, thus the approximate solution is UH of x, which is summation from I equals 1 to 3. You know, n is 4, right? So n minus 1 is 3. U1, UI phi I of x like this. Okay. Thus, I mean, this solution approximates, this solution approximates the exact solution. Since we have a second order equation, we can, by double integration, by integrating twice rather, the solution approximates the exact solution, which is u of x, which is equal to half into x minus x squared. Okay. But I mean, this is never complete until, I mean, this is never complete until we see the Python code as usual. So let's go for that. So see the Python code here. Um, Okay. I mean, you can find this on Facebook. If you follow me on Facebook with my full name, you find me, you can find it there. You can copy the code out and play with it. So we have the setup for finite element in one dimension. So if you look at from line 17, 18, we have h defined as 1 over n as expected. We have the x value. It's from 0 to 1 in n plus 1 divisions. Okay, then we have lines 21 and 22 where we define our K and F. From line 24 uh, to 39. Actually, the function is defined from line 4. That's we are defining the final element in one dimension to 39. So you have all the necessary thing there. So you compute the FEM solution with n equals 10. Well, if you choose n as 10 as number of elements here, and then the exact solution is given in line 46 for comparison, then we can also talk about the error here. And then if you run this, you see what that brings, that it gives a very good approximation. The numerical solution gives a very good approximation of the exact solution, which has been found to be what we just did. U of x equals half x into x squared, like that. So that goes. Um, we take it back here and as we try to round off. So from all we've seen, right, we can say that this example illustrates how finite element method systematically transforms a PDE into a solvable system of equations. The method extends naturally to high dimensions in 2D, 3D using elements like triangles and tetrahedra. So that's what this has been about. Okay. So, I mean, you can try this for heat equation. Okay, let me just say practice question, right? Practice question. Practice questions. Try to solve heat equation, wave equation using the finite elements method. Finite elements method. All right. So if you have subscribed, thank you so much for that. If you have not, you want to surely do that. If and hit the notification bell so you can always get alerted each time a new video is released. Then don't forget to comment. Let me know your attempts at solving this problem. And let me also know if there's a topic you'd like me to teach, a problem you'd like me to solve. Then like and share so that more people can have access to this great content. Till I come your way again, keep doing math right. Bye.